Okay, so guys, the squares and surface plates part of this lesson, um, I think is one of the most important bench work lessons that you can learn. Um, let's start first with the surface plate, just so that the easiest part of this is covered. Now, when you go into your Unit 8 and you look at the information on surface plates, the description on, again, this is Technology Machine Tools 7th edition. The definition under surface plates says a surface plate is a rigid block of granite or cast iron, the flat surface of which is used as a reference plane for laying out, setting up, and inspection work. Surface plates generally have a 3-point suspension to prevent rocking when mounted on an uneven surface. So that's on the underside, okay? So we work on the top of the surface plate. On the underside, there'll be 3-point suspension, triangular, to prevent any rocking, especially if we have an uneven surface. You can still get cast iron surface plates, but there are some disadvantages. So just take note here in your book with regards to the advantages of granite surface plates. So it says here, granite surface plates have many advantages over cast iron and are replacing them in many shops. So they're not all replaced. There's still shops around my place that use granite surface plates, but there are some disadvantages to them. But the granite surface plates are manufactured from gray, pink, and black granite and have several degrees of accuracy. So the accuracy, it's not just about the smoothness, right? So when these granite surface plates are manufactured, they're cut and then they're lapped smooth, like glass smooth, right? But just because something is smooth, it doesn't mean that it's flat, right? Because we can create a smooth angular surface, right? So a granite surface plate is not only smooth so that it will act as a reference plane to set a height gauge on or to set material on to measure off of, but it has to be accurate in size, right? I should be able to take an indicator, a plunge indicator on one corner of that surface plate and move that. So if this were the surface plate, plunge indicator on the corner and move that indicator corner to corner on that surface plate, and that indicator should not move. Now, a plunge indicator, typical plunge indicator will measure to 1/1000th of an inch, 3 decimal places, 0.001. Granite surface plates need to be accurate, generally speaking, from one corner to the opposite corner to at least 0.2 of a thousandth of an inch, 0.0002, to maintain any sort of accuracy when it comes to measuring. So if a granite, imagine if we had a 3-foot wide granite surface plate, the corner to corner measurement is going to be larger than 3 feet, right? So if this is our granite surface plate, right, and this is our 3-foot measurement right here, then the measurement from here to here is going to be greater than 3 feet, because in a triangle, the hypotenuse is always the longest side, right? So from this point here to this point here needs to be accurate to at least 0.2 of a thousandth of an inch. So if that's the case, what's the accuracy from here to here, right? From this point to this point, or from this point to this point, or this point to this point. So if the greatest amount of inaccuracy is 0.2, then any positions closer to one another is going to have a smaller degree of inaccuracy, right? So that's why having the granite surface plate, manufacturing those granite surface plates to this type of accuracy is so important, because typically we're not going to have a piece of material that sits on our surface plate and encompasses the entire surface of that surface plate, right? It's going to be to set up a height gauge or an angle plate and a height gauge inscriber or something. So the inaccuracy is going to be minimal, almost immeasurable, right? So that's what we want to consider when we're talking about granite surface plates. The granite, it's rock, right? So the lifespan of that granite surface plate is going to be far greater than the lifespan of a cast iron surface plate. And notice, guys, in your book, the advantages of granite. So you will have to know this, just telling you in advance. Granite surface plates are not appreciably affected by temperature change. You know that steel can expand and contract based on temperature. Granite does not. So there's a huge advantage right off the bat, especially if your shop, a lot of shops don't have air conditioning, right? Or they don't have proper heating in the winter. So you can imagine even just condensation, and temperature change is going to affect a cast iron surface plate. It won't affect a granite. A granite will not burr. Therefore, the accuracy is not impaired. So if you dropped your workpiece on your on your cast iron surface plate, it's going to dent. And if you dent material, if you create a dent concave in material, it's going to create a convex dent or hill of material on the surface, right? You're going to feel that burr. That doesn't happen on granite. Now, mind you, if you drop something, you can chip the granite, but you at least won't create a burr, right? And have any inaccuracies after that. They're not magnetic. Huge advantage, right? For a machine shop. Rust proof. There's a big one. We talked about condensation in a shop. So if you don't have proper heating, you don't have proper air conditioning, your condensation levels are going to be like this, right? And guaranteed, you're going to have some rust issues with cast iron. And abrasives will not embed themselves as easily in the surface, thus they may be used near grinding machines. So you will see often in machine shops, especially if you have a large surface grinding area where a lot of surface grinding is done and then parts are checked, you're going to see granite surface plates throughout, because you can literally just wipe those granite surface plates, clean them, and they're just back like glass again. But over time with cast iron, that small shavings and burrs and metal, if you took a block of steel and set it down on that cast iron surface plate after you've been grinding all day, you can embed those chips in that cast iron surface plate, but you can't in the granite. Okay, so there are some, you'll be answering some of these questions with regards to surface plates in the questions in the back of this book. But if you're going to take something away from the surface plates, guys, they're more common, they're more reliable, their lifetime is far longer than that of cast iron, and they're expensive. Okay, so I will tell you that they are expensive to buy a surface plate. But you know what? When you get into the shop and you start working with some of these bench tools and you start working with the granite plate, at least you'll have a little bit more respect for it, right? So it's not just a $50 piece that gets placed down there, and maybe you never thought about the accuracy of it. But if you realize that this might be a $600 or $700 piece of stone, it might be a $1,200 piece of stone that is ground and lapped to extremely tight tolerances and is reliable for all of your measuring and bluing and scribing, well, now your respect for it goes up a little bit. Okay, I do want to just touch on the square. So Patrick Chin, who created this video for me, he made mention of there's different types of squares. And he talked a lot about the machinist square, but I do want to just clarify one thing, because we can just say machinist square and you just think of a steel square, but they are all given different names. So that square that you saw in the video, that he said was a machinist square. We actually call it a solid square. Okay, we call them a solid square. Um, it is a machinist square, but it can be a little bit misleading. And the reason why it can be misleading is a lot of times, if you look on page 69 of Unit 8 there, it shows a picture there of the combination set. And sometimes in the shop, a machinist will ask for his machinist square or his toolmaker square. And what he's referring to is the square head and the steel rule. Okay, those two components, he'll often refer to that as a machinist square or a toolmaker square. So I just want to make, for clarity, if you look at figure 8-3 in your book, okay, it shows a solid square. It's got the heavy base and then the blade. We just call that a solid square. Okay. But next to it, you see the combination square. So the top is a combination set. The combination square is, again, typically called a machinist square or a toolmaker square. So let's just call them by their proper names. Okay, so figure 8-3 with the heavy rectangular base and the rectangular thinner blade, solid square. Okay, the combination square is adjustable, right? And you can see it there. It has a little screw. You can loosen it, slide it up and down the blade, and then tighten it again. So this is a great square for allowing you to not only square up a part, but also locate a measurement, because that steel rule is a rule. We don't call them rulers, we call them rules. Okay, so that steel rule has your fractional measurements on it, and you can locate a position and have something set square. But if you just turn over the page, and this is again why it's important that we understand the different types of squares. Maybe is it on the other page there? Oh, sorry, go back to the first page, 68, beveled edge square. So a beveled edge square is similar. A beveled edge square is similar to a solid square, but let me just show you the difference. So imagine that. So this is your square, your solid square. That's your base. Okay, and then you have the blade comes out like this. Okay, this is your solid square, and what square is this here? Okay, that's 90 degrees. This is 90 degrees. Okay, so this, you can inside or outside, is 90 degrees. Now some of these squares, the blade sits proud of the base like that, and some of these squares, the blade comes right down to the bottom of the base. But in both cases, that solid square is square on the inside open corner and on the closed outside corner. Now looking down from the top, what this looks like is like this. This is the blade, and this is the base. Can you see that? So that's if we're looking down on the top of the square. Notice that this end is a square blade. Okay, so this is also square, right? So if I will say zoom into that blade, okay, that's your blade right there. Okay, so this, all four of these corners are square, right? These are all square. Okay, so this is what this blade looks like, the solid square looks like from the top down. Now, we have another type of square called a beveled square. The difference with the beveled square is typically this is all manufactured as one piece. There's not a base and a blade. It's one piece. Okay, it's manufactured as one piece. But you'll see here will be a bevel. And how that looks from the top, I guess I should draw it a little bit more accurately, is like that. So if we blow this up a little bit, So looking down from the top, that's what the blade looks like. Okay? The blade is beveled. This is the bevel, and that's what it looks like from the top down. It actually comes to a point part. We can put a regular square up against a surface. Okay, so this is our regular square. We'll put our regular square here. Okay, the blade of our regular square. And we've got this round part. My artistic skills are amazing. You don't have to tell me. Okay, so we've got the beveled square. Comes up against the side of a part, and it creates line contact. So you have the least amount of material on this beveled square touching your part. It is going to show you more accurately if this part is out of square compared to using this solid square. Because the solid square, even though anytime a line comes into contact with a surface or a circle, right? Anytime a line comes into contact with a surface, a circle, it only touches at a point, right? The tangent point. Well, this solid square is really only touching in one place. But where is it touching? Is it touching over here? Is it touching in the middle? Is it touching over here? And if I look through that square touching that surface, is the square this way, this way? Is it straight? Right? Do I have it lined up perfect? Where is it touching? And what'll happen is the light that you should be able, if it's not square, you should see light through here. But it's more difficult to see light through here because you don't know how that square is sitting exactly or where the tangent point is. So if you need to, now don't get me wrong, the solid square is accurate and reliable. But if you want to spend another 40%, because you're buying your own tools for life, buy a beveled square. Buying both is great, but the beveled square is your longer life investment, right? Because you're going to be able to check more accurately across the board with a beveled square than a solid square. But odds are you're going to see more of these in industry. They're cheaper, they're faster to replace, cheaper to replace. And you can eliminate some of this problem by making sure that your square goes against a backstop, or you can use an angle plate or something else to make sure that square is touching as close to center as possible. So there are little tricks, but just letting you know the difference between those two squares is that beveled edge. Solid square doesn't have it. It's flat. Beveled edge has that point that creates line contact when it comes into contact with the part that you're checking for square. Page 70, figure 8-6, guys. So it sounds kind of strange here. It's called a cylindrical square. So we want to make sure that we don't misunderstand what it means when we're talking about a square. Okay, we're not talking about a shape, right? So when we talk about something being square, we're not talking about a square. Okay, that's not what we're talking about. We're talking about something that is 90 degrees, perpendicular. That's why we can have a cylindrical square. So if this is my surface plate, which we know is an accurate reference plane, and I have a piece of material sitting on my surface plate that I want to know if this bottom flat edge is square to this surface. Maybe the customer said to me that this surface A has to be square to surface B within 0.02 of an inch. Well, I just manufactured this part. if I sit this surface, we'll call this surface B, if I sit that on the granite table, then I can put a square up against the side here, or a solid square or a beveled square, and I can check and see if there's any light shining through. Now, remember the reason why we kind of step to the beveled square, right? It creates line contact, right? But an even more precision type of square is the cylindrical square. And the reason why that's far more precise is because the cylindrical square from the side looks like this. And I can put it up against my part. That's my part. And it's all sitting on the granite table. So this is my part. And this is my cylindrical square. It's a square because this surface is, I don't like to use the word perfect, but as close as it can possibly be to perfectly perpendicular to this surface. Looking down from the top, the cylindrical square is a circle, right? It's a cylinder all the way down. So a cylinder from the side looks like a rectangle or a square, but from the top it looks round, right? And we can get kind of a better perspective of that if we try and draw an isometric view of a cylinder, right? So this surface down here is perfectly perpendicular to the side of the cylinder. Now, if you look straight on the front of this, it's going to look like this, right? If you look straight down the top of this, you're going to see it as a circle. But if you look at it isometrically, you see the cylinder shape. A cylindrical square does a very similar thing, but to a far higher level of precision as a bevel square. A bevel square creates line contact between your part and the square. Cylindrical square, this whole surface from here to here is line contact with your part. So if your part is square, perfectly square, quote unquote, perfectly, okay, then you will see no light between the cylindrical square and your part. No light will shine through. The nice thing with these cylindrical squares is they're made with such high precision. If your part is relatively square but has some imperfections, you might see a little bit of light somewhere here. Maybe you'll see a little bit there, maybe a bit there, maybe a whole strip from here to here. You see light between the two. So any imperfections on your part, you will see light because that cylindrical square is creating line contact from the top of that square to the bottom with a great amount of precision. Okay, so our squares kind of have levels, right? So your typical solid square, it's a great reliable square to make sure you can scribe lines with it. You know, you can make sure a part is, you can rough square up the head of your mill with it, right? You can sit it on the table, get the head quickly square by using a square, tighten up the gibs, and then start bringing it in a couple thou here and there, and it's good. You have your combination square, the one that we want to try not to call her machinist square or toolmaker square. Okay, so we have our combination square where the square can slide up and down the steel rule so that you can not only check squareness, but you can actually make check measurements and scribe lines at specific measurements. Then you have your beveled square, which is a little bit more accurate, a little bit more expensive. We have some other squares. You're going to get that in your assignment. But then we have our cylindrical square, right? This is the square that you want to make sure is covered and put away. You don't want to leave it out on the table. You don't want that to get accidentally bumped on your watch because that's not cheap to replace.